Alright, thank you very much for tuning in. This begins tutorial 5, interfacing a 7-segment display with a PIC microcontroller. All credit goes to Khaled Mogdi. Once again, not trying to take this content and fill my channel up with it. I'm genuinely interested to learn PIC microcontrollers. I certainly couldn't create something like this at the present time, so I'm very thankful that he took his time and created something like this. The grammar isn't perfect, but the content is really great, and I find that I'm really learning a lot as I read these tutorials. So I do appreciate them. In this tutorial, you'll learn how to do 7 segments displays work. In this tutorial, learn how to do 7 segments displays work. And to interface 7 segments display with PIC microcontrollers. The 7 segments display needs a little bit of programming effort, and it's pretty easy and straightforward. So let's get started. Once again, if I've got the time, maybe I can include this in the description below, or a comment that I pin to the top of the video, and add some timestamps so it's easier to navigate through the video. Well, I've certainly been talking a lot, and it takes a lot of time up in the video, but one thing I'd like to say is that this isn't particularly interesting to me so much as it's going to start covering a lot of the coding, and that's interesting. Components needed for this tutorial: the PIC chip he's using. I can't remember which one he's using. So here's a Google search of the pin of the integrated circuit he's actually using. I might want to pause that. Then a breadboard, a jumper wire pack, 330 ohm resistors, 400 megahertz crystal oscillator. I watched some other PIC programming videos that were sort of suggesting that a 4 megahertz oscillator is not entirely critical. I shouldn't comment too much further. They were setting up the RC option, resistor capacitor. Seems to work fine, but anyway, 5-volt regulator, 9-volt battery or any power supply source, a PIC Kit 3 programmer. What are 7-segment displays? The 7-segment is a simple electronic device that includes 7 LED bars arranged in such a way that represents decimal numbers, 0 to 9. It also can be used to display hexadecimal digits, 0 to F. However, these devices actually have an 8th LED that represents the decimal point. The 7 segments display are being used for simple display tasks within multiple applications. Example: heaters, boilers, DVD players, audio players, wearable gadgets, digital locks. Learning how to interface the 7-segment display will help you create user-friendly applications. Let's imagine that you are creating the X machine, which could be a boiler, for example, or whatever. Your device is supposed to show the user its current temperature value. Though you can possibly write the temperature's binary value to an output port and hook some LEDs to show this number, well, you can imagine how terrible this could be. X machine temperature is, I guess there's 1, 2, 3, 4, 5, 6, 7, 8 LEDs. Well, it's 43. It's annoying indeed. Your machine could only be shipped to expert users with knowledge in digital systems. However, it's not guaranteed to sell any pieces at all. How 7 segments actually work. There are two types of 7-segment displays for each model, namely common cathode and common anode. This refers to the internal connection polarity convention of the LED bars. The difference is shown in the figure below. So there's a normal LED where the power is going to the anode through a resistor and back to ground. Okay, I think I've seen these before, so I think it's straightforward. In this case, the LEDs all share a common cathode, which I suppose is the ground, and in this case they all share a common anode. As you may have noticed, these devices are basically some LEDs hooked together in DIP packages, hence the ease in operating / interfacing 7 segments. It's no more than some LEDs could be hooked to input-output ports via 330 ohm resistors and be easily controlled. However, you should pay attention to the following couple of pints. I think that means pins. Common cathode, 7 segments. The cathode lead of all LEDs are connected together internally, so you'll have to connect this cathode lead to ground, and the anode leads to an input-output port. Consequently, the activation switching of the LEDs will be achieved by setting right 1, the respective ports pins active high. So I'll look back at the picture. Common cathode. So this is the common cathode. I guess that's sharing a ground. Common anode, 7 segments. The anode lead of all LEDs are connected together internally, so you'll have to connect this anode lead to 5 volts VDD, and the cathode leads to an input-output port. Consequently, the activation switching of the LEDs will be achieved by clearing right 0 the respective port pins, active low. So here's the common anode, probably hooked up to 5 volts VDD. We'll be using the common cathode 7 segment for this tutorial, as the active high positive logic is a much more straightforward convention. How to interface 7 segment displays. The first step for interfacing a 7 segment display is to construct the sequence table. This table function is to provide the mapping between numbers sequence and the corresponding output bit pattern. Create a simple table similar to the one below. Go through the numbers from 0 to 9 and mark the LEDs that should get activated to display the respective decimal number. Note to self to just pause this screen and study it. Okay, well this makes sense. So number 0 would be all of the outside LEDs, which would be every LED excluding G, A to F excluding G. Number 1, he's saying B and C. Okay, so I take it this is probably like a binary number, and for reasons I suppose I will find out in a minute, there's a corresponding hex code. Well, I'll just try it. So take number 0, A, B, C, D, E, F. Okay, so this number 0, the segments would be 1, 1, 1, 1, 1, 1, 0. So I typed this into a binary to hex converter, and 7E is the result. But that's not what he's writing here, so I better continue reading. You should also note that the bit pattern for 7 segments is 7 bits, but the output ports in our controller are 8 bits in width. Example, port B, port C, which means we must perform right justification or left justification. The coding shown above is left justified codes, which means the LSB bit 0 is assumed to be low. 0 for all the 10 digits patterns. The following examples will show you why the bit pattern for digit 1 is 0 times 60. Okay, so once again, digit digit 1 is just B and C. Okay, well, I'm jumping around, but I'm going to go back to number 0 here. Everything for 0 was highlighted around the outside of the 7-segment display except for G, and he's saying the hex code is FC. But then he's saying that basically you tag on a 0 at the end for all of these numbers because it's like left justified. So I went to this hex converter and I just added another 0, hit convert, and it's FC. Well, that's what he had. Okay, so I'll read this picture. The 7 segments bit pattern is 7 bits, but port B register is 8 bits. So we perform left justification. For example, the bit pattern for digit 1 is just B and C were lit up. B and C. And then they tag on a 0. So port B is 6, 0. So it checks out on the binary to hex converter. Result is 6, 0. By repeating the process for all the 10 digits, you'll end up with a table as shown in the first figure. This is the final patterns data array, which we'll be using in the programming process afterward. The final array will be as follows. 1, first line of code, I guess, unsigned character segments underscore code square brackets 10 equals 0 times FC, which I guess is number 0, 1, 2, 3, 4, 5, 6, 7, 8. Yes, I've got to scroll over. That's number 9. This continues. Lab name, counting with 7 segments display. Lab number 3, lab level beginner. Lab objectives, learn how to use input-output ports to control interface a 7-segment display. Learn how to interface 7 segments display to print out numerical data in a user-friendly fashion. Coding, open the MPLab IDE and create a new project. Name it 7 segments underscore counting. If you have some issues doing so, you can always refer to the previous tutorial using the link below. Set the configuration bits to match the generic setting, which we've stated earlier. And if you also find troubles creating this file, you can always refer to the previous tutorial using the link below. Now open the main.c file and let's start developing the firmware for our project. Our task is to display the decimal digits 0 to 9 on the 7 segments for half a second for each number. So we must first define the bit pattern array and a counter variable to index our data array. We should also configure an input-output port to be an output port. Let it be port B, thus the main function code will be as shown below. Void main, void, and this stuff I have to research and understand better. Unsigned character, segments underscore code equals 10, equals all the different numbers. Unsigned character, counter equals 0, semicolon. Trice B equals 0 times 0, 0. Set all pins to be output pins. Port B, initially clear all the 8 pins, so send them all to 0. While 1, port B equals segments underscore code counter. Then there's a delay, counter plus Well, it's as simple as it seems to be. Now the problem I have is not all of this coding has been explained, which maybe is my lack of understanding of C language. So maybe that's my fault. Cross your fingers, hit the compile button, and we're done with the firmware. Simulation. The schematic for this lab is shown below. Just create a similar one in your simulator. Of course, you can ignore adding the 330 ohm resistors only for the simulation phase, the project. Okay, so I guess if you're going to draw this in the simulator, you don't have to add these resistors. I guess he does. I guess this is what a common cathode LED looks like. The key to properly connect the 7 segments display in your simulation environment is to know the letter of each pin, A to G. This is easily achieved by pointing your mouse to any pin of the 7 segments 8 pin, and it'll tell you the name at the bottom notification bar as shown below. After connecting everything up in your simulator, you'll have to double-click the MCU chip and point to the firmware code.hex file to make sure to simulate your project at the same oscillator frequency used in the code. Otherwise, the timing diagram will be messed up. Prototyping. You should have created the basic prototyping setup, which we've demonstrated previously. If you've any troubles doing so, you can refer to that previous tutorial. The connections for the 7 segments pins should follow the table below. You can discover the letter of each pin on your 7 segments DIP package using the multimeter's LED test mode. Practically identify each of the pins to know which one is A, B, C to G, then follow this table shown below. Connect your programmer's ICSP port, flash the code, plug the power supply, and test this out. The final running project in case you're curious. So he's created a video. Just for reference, this in-circuit serial programming port, well, that's what it stands for. I don't know if simply by powering it on it begins. I think it probably does. He has the downloadable files. And that looks like the completion of tutorial 5.